Welcome back to the deflection and cracking problem. In the previous class, we started a problem to calculate the deflection. So as we discussed, the total deflection is immediate deflection and long-term deflection. So on long-term deflection is further divided into deflection due to shrinkage and the deflection due to creep of concrete. So we calculated what was the immediate deflection. I think it turned out to be 7.45 millimeter after the calculation. So this part is done. The next step we are going to do is ACS, that is the deflection due to shrinkage of concrete, ACS. So if you open page number 88 of the code book, that is annexure C on page 88, if you look at C 3.1, the equation says the deflection due to shrinkage of concrete is ACS equal to, that is equal to K3 S and L square, CS L square. So where K3 equal to 0.50 for a cantilever beam. So again you are going to get under C 3.1, that is annexure C 3.1 on page 88 of the code book. So again this is C 3.1 page 88. Okay. So K3 equal to 0.5. Next, what is psi CS? Psi CS is curvature, that is shrinkage curvature. Shrinkage curvature, that is psi CS equal to K4 into CS epsilon CS divided by T. So if I call this as equation A, I am going to call this as equation B. So what is K4? So as per the code, K4 equal to 0.72 PT minus PS square root of PT, that should be less than equal to 1 if 0.25 is less than or at most equal to PT minus PC, and that is less than 1.0, and that is equal to 0.65 PT minus PC divided by square root of PT, and of course that value should be less than or at most equal to 1 if PT minus PC is greater than equal to 1.0. So I am going to call these two equations as equation C. I am going to make use of only one of those two equations. So that depends on the value of PT minus PC. PT is nothing but percentage of tension steel and PC is nothing but percentage of compression steel. Percentage of compression steel. So now what I do is I am going to find out what is the value of K4. So by knowing PT and PC, then once that is done, epsilon CS is the shrinkage coefficient. Shrinkage coefficient is 0.0003 for concrete at 28 days. So that is a value you need to remember. For if you want to know where exactly it is located, so what you can do is you can go to page number 16 of the code book. On page number 16 of the code book, under 6.2.4.1, it says, in the absence of test data, the approximate value of the total shrinkage strain for design may be taken as 0.0003. That is the shrinkage strain epsilon CS. So here, therefore, PT equal to, let me find out what is the percentage of tension steel first. That is 100 AST divided by BD. So that is 100. AST is, we have 4 bars of 20 mm diameter. Because this is cantilever, top surface is subjected to tension. So these are tension reinforcements. So that is 4 multiplied by pi by 4, 20 square is 1256.64 is the area of steel, and B is 300 and the effective depth is 550. That is equal to, let me see what is the percentage of tension steel according to the calculation we got. That is here it is. That is 0.762, 0.762, and percentage of compression steel equal to 0%. 0%. And shrinkage strain epsilon CS equal to 0.0003 as per 6.2.4.1, page 16 of the code book. Now, by substituting the values of PT and PC in equation C, see whether we use this equation or this equation of C depends on what is the value of PT minus PC. So what is the value of PT minus PC? PT minus PC is 0.762 minus 0.00, that is equal to 0.762%. So here PT minus is 0.762. So this is 0.25 is less than 0.762, and it is less than 0.762 is less than 1. So I can make use of this equation to find out what is the value of K4. So in case if it was greater than 1, then I would have used this formula, greater than equal to 1. I would have used this formula to find out what is K4. So in this case, what in case PT minus PC is less than 0.25? In such cases, we need to increase the percentage of tension reinforcement. That is not adequate to take care of the deflection due to shrinkage. So we need to increase. So in this case, I am going to use this formula. So K4 equal to 0.72 times PT minus PC is 0.762, square root of PT, that is 0.762. That is equal to K4 equal to 0.762 629 is the value of the constant K4. Of course, that is less than 1. That should be less than 1. In case it exceeds 1, then we have to take the maximum value of K4 as 1. So now we have this K4 value. We know epsilon CS, we know D, that is a total depth, that is equal to 600 millimeter. So by knowing these three values, by substituting the values in equation B, we can get what is the shrinkage curvature epsilon CS. By substituting the values, in equation B, we get shrinkage curvature epsilon CS equal to K4 is 0.629 into epsilon CS, that is the shrinkage strain, that is equal to 0.0003 divided by D, that is the total depth, which is equal to 600. So after solving this, we are going to get epsilon CS, psi CS, this is psi and this is epsilon. So psi CS equal to 3.145 into 10 to the power of minus 7. That is psi CS. So once that is calculated, so the next thing I am going to do is I am going to substitute the values in equation A. So once I substitute that, I am going to get what is the deflection due to shrinkage of concrete. Now, by substituting all the values in equation A, we get ACS equal to K3, that is equal to 0.50 for a cantilever beam. Psi CS is 3.145 into 10 to the power of minus 7, and the next value is L, that is the length of the cantilever. So length of the cantilever is 3.5 meter. So 1 second, let me cross check that. That is 3.5 meter. That is 3,500 millimeter square. Therefore, ACS equal to 1.93 millimeter. That is the deflection due to shrinkage of concrete, which is equal to 1.93 millimeter. So if you come back to this equation, so we have this, we calculated this. This was 7.45 millimeter according to our calculation. We calculated this just now, which is 1.93 millimeter. The next step is we need to calculate what is ACC. That is the deflection due to creep of concrete. Next, let us find out that. Due to creep of concrete, that is ACC. So when it comes to the deflection due to creep of concrete, that is represented as ACC is nothing but the creep of concrete that is due to permanent load. We need to find out what is the deflection due to creep of concrete, and we are going to call this as PRM, that stands for permanent. If you open page number 89 of the code book, so the code book says the creep deflection due to permanent loads, that is ACC permanent, may be obtained from the following equation. So what is the following equation? ACC permanent equal to AICC permanent plus AI permanent. AI, I think it is within bracket, AI permanent. So what is this? ACC is nothing but, as per the code, it is ACC due to permanent, that is permanent load. So this is the total deflection. Total deflection is nothing but the immediate deflection due to creep of concrete plus long-term deflection due to creep of concrete. Okay, those two things we are going to get due to permanent load. So due to permanent load and not the live load, we have to take out the live load. So to get this, okay, and that should be, and this is not plus, this is minus. Next, AI permanent. So once we have that total load due to immediate and also due to creep, we have to take out the deflection due to immediate deflection due to permanent load to get the deflection due to creep of concrete under permanent load. So now we need to find out this first, okay, and this one next. Deduct this from this to get this and put this value here to get the total deflection. So if you open page number 89 under annexure C4, that says deflection due to creep, that is C4 page 89. So the code says the creep deflection due to permanent loads ACC permanent may be obtained from the following equation. One is ACC permanent, that is the total deflection due to creep due to permanent load, that is equal to AICC permanent, that is the immediate deflection and also the deflection due to creep under permanent load, minus AI permanent, that is the immediate deflection due to permanent load. Okay. So in this case, if you go further in the code, it says AICC permanent. What is AICC permanent? It says initial plus creep deflection. Initial is nothing but immediate deflection, and creep deflection due to permanent loads obtained using an elastic analysis with an effective modulus of elasticity. Here it is, we are not going to make use of EC. We know EC is the modulus elasticity of concrete, that is given by 5000 root of FCK. Instead of using that value, we need to make use of the effective modulus of elasticity, which is ECE. What is ECE? Again, if you look at the code, it says EC divided by 1 plus theta, where theta being creep coefficient. So first we need to find out EC. Afterwards, we need to find out what is ECE to find out what is the effective modulus of elasticity by taking the creep coefficient theta equal to 1.60. So theta equal to 1.60 for concrete at 28 days. So I am going to make use of that value to find out what is EC and what is ECE. If you go next, it says about AI permanent, as I explained, it is the short term or immediate deflection due to permanent load using EC value. When you find out this deflection, you need to make use of ECE, that is the Young's modulus, effective Young's modulus. If you are finding this deflection, we need to make use of EC value, that is the Young's modulus as per the code, that is equal to 5000 root of FCK. So we will go one at a time here. So I am going to call this as equation D. That is equation D. So let us find out first what is AICC permanent. We know the formula for the deflection of a cantilever under UDL and the cantilever of length L, deflection is given by WL to the power of 4 EI, 8 EI, if you remember. And this is the formula we made use of here. And we are going to make use of the same formula to find out this and this. And what is the difference? This will change. This will become ECE when you are finding out this, and this will become as usual EC when you are doing this. And what is this? I is I effective. How to find out? Yes, it is given in the code book, I effective. Okay. So let us go one at a time. We are trying to find out what is AICC permanent. So in this equation, so what I can do is I can split up this equation, WL square by 2 and L square by 4 EI. So what is WL square by 2? That is the maximum bending moment which occurs at the support for this cantilever under UDL. So that is M L square by 4 EI. Then what is M? Yes, that is a maximum bending moment. So what is the maximum bending moment? Here we should not consider the total service load, instead we should consider the total service permanent load to find out these two deflections. Okay. So if I read out the problem which I wrote in the first class itself, so the problem says a cantilever of 3.5 meter, span is 300 millimeter wide and 600 millimeter deep, that is capital D. It is subjected to a maximum bending moment of 125 kilonewton meter due to uniformly distributed service loads. The problem says service loads. When we say loads, it includes both permanent load and live load. Okay, of which 50% moment is due to permanent loads. So total moment is 125 kilonewton meter due to service loads, out of which 50% is the permanent load moment. So 125 kilonewton meter multiplied by 0.5 times, that is 62.5 kilonewton meter is the value we need to make use of here to find out the deflection. Is it clear? So let us go one at a time. So let me write this equation. We have AICC permanent equal to, I am going to write that equation, M L square, and instead of E, as per the code, I need to make use of ECE. It says, again I am going to reread it, AICC permanent initial plus creep deflection due to permanent loads obtained using an elastic analysis with an effective modulus of elasticity, that is ECE. So it is 4 ECE, and what is the value of moment of inertia? That is again I effective. So let us go and find out what are these values. So MS is the moment, M equal to moment due to permanent load. How much is this? As per the problem given, so M equal to 50% of total moment, that is equal to 50 divided by 100, that is equal to 125. M equal to 62.5 kilonewton meter. Okay. So next, this is calculated. L is the length of the cantilever, which is 3.5 meter, that is equal to 3,500 millimeter. That is L. So L equal to 3.5 meter, that is equal to 3,500 millimeter. Next, what is ECE? Before finding ECE, first thing I am going to do is find out EC. EC equal to 5,000 root FCK, that is equal to 5,000 root 20. So that is already calculated in the previous step. Let me see what is the value. 22,361 kilonewton, Newton per millimeter square, where FCK is the concrete characteristic compressive strength of concrete at 28 days. Therefore, ECE, again it is given in the code book, okay, on page 89. ECE is nothing but EC divided by 1 plus theta, where theta equal to creep coefficient, that is equal to 1.6 for concrete at 28 days. Okay. Now I am going to substitute this value here. Therefore, ECE equal to, ECE is 22,361, 1 plus 1.6, that is equal to 8,600 Newton per millimeter square. 8,600 Newton per millimeter square. Next, once this value is obtained, this is known now. What is the next step? We need to find out what is I effective. What is I effective? Again, I will go back to the code. Okay. So, if I go back to the code under C21 on page 88, to find out IFF for I effective, IR 1.2 minus mr divided by m z divided by d 1 minus x divided by d bw by b. So if I call this as equation C, let me call this as equation D. I think A, B, C, I think I call this as equation D. If I call this as equation D, I can call this as equation E. So I am going to call this as equation F. Okay. So coming back to this, what is IR? To find out IR, so what is IR? IR is the moment of inertia of the cracked section, moment of inertia of the cracked section. So before that there is one more condition which I forgot to write for this equation, that is IR should be less than I effective and this should be less than I gross. Okay. So to calculate IR first, so I need to find out what is the moment of inertia of the cracked section. If I call this as the neutral axis, let the neutral axis depth be x from the bottom compression edge. I need to convert the steel into equivalent concrete area by multiplying this steel area by the modular ratio m. So I am going to replace this with the equivalent concrete area, that is equal to MAST. This is B, 300 millimeter, and this is 550 millimeter, that is the effective depth. Okay. So first thing we need to do is to find out IR. We need to find out what is M. What is the modular ratio? To find out the modular ratio from the previous step example, that is the previous part AI. So modular ratio is the Young's modulus of steel material divided by the Young's modulus of concrete. Here in this case, we should not use this EC value, instead we should use ECE value, that is 8600 Newton per millimeter square, to find out the Young's modulus of, to find out the value of M. So now modular ratio M equal to Young's modulus of steel divided by effective Young's modulus of concrete. So steel is, we know, 2 multiplied by 10 to the power of 5 Newton per millimeter square. ECE, what is ECE? That is 8600 Newton per millimeter square. So what is the value of M? Let me look at my notes. That is 23.26. 23.26 is the value of modular ratio. Okay. So after all, what is the moment of inertia of a given section about a given axis? that is moment of inertia of this about this axis plus moment of inertia of this concrete area about the same axis, add them together. Okay. So, of course, we are going to ignore the tension part of the concrete. Instead, as I said, we are going to make use of the equivalent concrete area which is calculated by converting the steel into concrete. Okay. So, before finding out the moment of inertia IR, that is the moment of inertia of the cracked section, we need to know what is the depth of what is the depth of the neutral axis, which is x. To know x, what we do is we need to equate the moment of area of the compression zone and the tension zone about the neutral axis. We will have only one unknown, that is the x value, and by solving that equation we can find out what is x. That gives the depth of the neutral axis. Once we know the depth of the neutral axis, easily we can find out what is the moment of inertia of the whole cracked section about the neutral axis. That is IR value. Once we know IR value, okay, MR is the moment of resistance of the cracked section. Again, as given in the code, we are going to make use of bending equation, and I am going to find out what is MR. I am going to show you that. And what is M? That is 62.5 kilonewton meter. Substitute. Z is the lever arm, which is given by D minus x by 3, and D is the depth 550. BW by B equal to 1 for a rectangular section. So, once we know all these things, substitute all the values here and find out what is effective, and make sure this I effective falls between these two values. Okay. And if this goes below this, consider this value. If this value goes above this, consider this value. But normally this value will be majority of the time between these two values. Okay. And let us proceed. We have M. Next thing is to find out what is X. Okay. Going further, to find out X, so by taking moments and equating moments of the area of the cracked section in both compression and tension zones about the neutral axis, If I do that, so let me take the moment of this area about the neutral axis. So what is this distance? This distance is D minus x. So that is MAST multiplied by D minus x. I am going to equate the moment to the moment of the area in the compression zone. That is Bx is the area of the compression zone, x by 2 is the centroid of that area from the neutral axis, distance of the centroid of that area from the neutral axis. So MAST, M is, so we just now calculated, that is 23.26, 23.26 into 1256.64, D is the effective depth, that is 550 minus x, which we don't know yet, and B is 300, x by 2. On further simplification, the equation gets reduced to x square plus 194.86x 107175 equal to 0. So on by solving the equation for x equal to minus b, that is 194.86 plus or minus b square 194.86 minus 4a, c is minus 107175 divided by 2a. Is it clear? Therefore, x equal to 244.14 millimeter. millimeter. So once we know x, the next step is to find out IR value, that is the moment of inertia of the cracked section about the neutral axis. Therefore, moment of inertia of the cracked section IR equal to, so by definition we know what is moment of inertia, that is the second moment of the area. So that is MAST d minus x square plus moment of inertia of this rectangle about this is BDQ by 3, that is BXQ by 3. So we know M, that is equal to 23.26, AST is 1256.64, D is 550 minus X is 244.14, 244.14 square plus B is 300 and X is 244.14 cube divided by 3. Therefore, moment of inertia of the cracked section is given by 41.90 into 10 to the power of 8 millimeter to the power of 4. Okay. So again, in the equation I effective equal to IR divided by etc. So in this we calculated what is IR. So what else do we need to calculate? M is, yes, is half the moment, that is half of 125 kilonewton meter, that is equal to 62.5 kilonewton meter, that is equal to 62.5 multiplied by 10 to the power of 6 Newton millimeter. Okay. Then what is Z? Z is the lever arm. Lever arm is the distance between the center of gravity of the compression force to the center of gravity of the tensile force. So what is that value? Because in case of elastic design, we are going to assume the triangular variation of the stress. So the lever arm is going to be D minus of x by 3, that is D minus of x by 3, that is equal to 550 minus x is 244.14 divided by 3. So Z equal to 468.62. 468.62 millimeter. Next, what is D? Yes, effective depth. So BW by B equal to 1 for a rectangular section, because BW equal to B. So only in case of this one T beam. So this value changes and this value will be greater than 1. So for a rectangular section it is 1 for a rectangular section. Then what is MR? And we need to calculate the value of MR. Again, if you go to the code book, page 88 under Annex C, under C.2.1, so it says MR is the cracking moment that is equal to FCR multiplied by IGR divided by YT. Okay. So YT, so let me know where exactly that value is located. That is 56.6 Newton meter. Okay. So MR equal to FCR IGR divided by YT. So this is FCR. So what is FCR? That is a modulus of rupture of concrete. So modulus of rupture of concrete FCR equal to 0.7 times root FCK, that is equal to 0.7 times root 20, that is equal to that value I calculated in the previous example. So that is equal to 3.13 Newton per millimeter square. Then what is YT? That is the distance of the extreme fiber from the neutral axis. So that is YT equal to D by 2, that is equal to 300. That is not D by 2, that is capital D by 2, 600 by 2, that is equal to, only 1 second please, 1 second. So code says YT is okay, this is correct. So YT is the distance of the extreme fiber from the neutral axis of the gross area. So gross area is 300 multiplied by 600. So 600 by 2, that is equal to 300 millimeter. Okay. So IGR, of course we have calculated IGR, that is the moment of inertia of the gross section. So how much? Yes, we calculated before in the previous step, that is 54 into 10 to the power of 8 millimeter to the power of 4. Okay. IGR is known here, FCR is known, YT is known, therefore MR equal to, FCR is 3.13 into gross is 54 into 10 to the power of 8 millimeter to the power of 4. yt is 300. So finally we are going to get the value of mr equal to 56.34 into 10 to the power of 6 Newton millimeter. Okay. And of course, m is half the value of total moment, that is 125 divided by 2, that is equal to 62.5 kilonewton meter. So if I go to that equation, I effective equal to IR divided by 1.2 minus mr by m z divided by d, 1 minus of x by d, bw by b. So we know all the values. So substitute all the values in that equation, okay, given in the code on page 88 under C.2.1, we are going to get the effective moment of inertia IFF equal to, by substituting all the values in the above equation I effective equal to I am going to substitute what is the IR value. So IR value is 41.90 into 10 to the power of 8. Next, 1.2 minus mr. mr is 56.34 into 10 to the power of 6 divided by m is 62.5 multiplied by 10 to the power of 6. Z divided by d, z is this value, live around 468.62. 468.62 divided by 550 is the effective depth, 1 minus, and the x value is 244.14 divided by d is the effective depth, and bw by b equal to 1. Therefore, I effective equal to 54.20 into 10 to the power of 8 millimeter. But what is the condition? It says IR should be less than equal to I effective, that should be less than equal to I gross. Okay. But here IR is 41.90, 10 to the power of 8, that is less than, what is the value? I effective is 54.20 into 10 to the power of 8, and that should be less than I gross, that is 54 into 10 to the power of 8 millimeter to the power of 4. Look here, this is not less than 54.54 multiplied by 10 to the power of 8, that is, this is not going to be satisfied. If that is the case, what is the value of I effective we should take? We should take the value of this. We have to take the moment of inertia of the gross section as the effective moment of inertia of the section. Therefore, IFF equal to 54 into 10 to the power of 8 millimeter to the power of 4. Okay, that is the effective moment of inertia. Okay, so once we have it, so we have the formula to find out the deflection. So we have the values in the above deflection equation that is, I am going to rewrite that formula AICC permanent, that is equal to MCL square divided by 4ECEIFF. Okay. So, by substituting this value, MC is half the value of the moment, that is called as M, that is 62.5 into 10 to the power of 6 into 3500 square. I am going to call this as M itself. So, divided by 4 into what is the effective Young's modulus ECE value, that is 8600 into 54 into 10 to the power of 8. Therefore, AICC permanent equal to 4.12 millimeter. 4.12 millimeter. The next step is to find out AI permanent. Next, to find out AI permanent. Again, I am going to make use of the same formula. So, by making use of the same formula, so AI permanent equal to ML square 4EC I effective. Okay. So, in this case, I effective. Look here, what is the difference? This is here we are using ECE. In this case, we are using EC value. Okay. Again, now the next step is we need to find out what is the deflection, that is the immediate deflection due to permanent load. So, what is M? Yes, that is 62.5 multiplied by 10 to the power of 6 kilonewton meter. So, as usual, when it comes to EC, so in this case it is effective moment of inertia. Here it is EC, that is EC equal to 5000 root of FCK as given in the code book on page 16. Okay. And what is I effective? This I effective is not going to be the same as this. No, it is not. The reason is, in this case, to find out what is modular ratio, we made use of the formula M equal to modulus of elasticity of steel divided by ECE. Okay. Because this is immediate deflection and also creep deflection. So, in this case ECE is a different value, okay, and as a result we got the value of M equal to 23.26. But for immediate deflection, to find out the value of M, we are going to make use of ES divided by EC, and we got the value of M equal to 8.94. If you look back in the problem, okay. So, using this value of M, we calculated the moment of inertia of this section. We got this value, Now, for immediate deflection, so what we need to do is we have to make use of this modular ratio, that is 8.94, which was calculated using EC value but not ECE. As a result, I effective will also change. When we calculated the initial deflection, when we made use of the I effective value, that I effective value should be used here, not this. Keep in mind. So, EC is different, I effective is different. So, I am going to find out what is IAI permanent using those values. So, by substituting the values, by substituting the values, in the above equation. See, when I say in the above equation, not this equation, instead I am substituting the values in this equation. Okay, above equation, AI permanent, that is the immediate deflection due to permanent load, equal to M is 62.5 into 10 to the power of 6 Newton millimeter, L is 3500 square, 4 into EC, it is not ECE, instead again I am repeating EC, that is equal to 5000 root of FCK, that is equal to 22,361, and I effective 22.97 into 10 to the power of 8. So, we have done calculation for this. If you go back and refer this step to find out what is AI, you are going to get this value. So, AI permanent equal to 3.73 millimeter. Okay. So, I got the value of AI CC permanent. This is immediate deflection and long term deflection due to creep of concrete as 4.12 meter. So, but what we need is only the creep of concrete deflection. When we need creep of concrete deflection, we need to minus immediate deflection, which is this. So, when I deduct this value 3.73 by 4.12, so I am going to get the value of ACC permanent, that is nothing but this ACC equal to 4.5 minus 3. It is, sorry, so there is some calculation mistake, I am going to correct. AI permanent is 3.73 and 4.5 minus of 3.73, CC permanent 4.12. Okay, that is ACC permanent is 4.5 minus 3.73. This value is not 1.93, 4.5 this ICC permanent is 4. This value I am going to change, I think this is 4.50, 4.50 minus of 3.73, that is equal to 4.5 minus of 3.73 is 0.77 millimeter. Okay. So ACC is calculated, this is calculated, this is calculated. Therefore, the total deflection, AT equal to AI plus ACS plus ACC, that is equal to 7.45 plus 1.93 plus it is 0.77, 0.77. So AT equal to the total deflection is 10.15 millimeter. Okay. This is the total deflection at the free end of the cantilever. Okay. It is a long-term deflection, not the immediate deflection, it is a long-term deflection. But we have to check whether it is within the permissible limit, that is permissible deflection. Is delta permissible equal to span divided by 250. So where did I get this value? 23.2a, page 37 of the code book. Please open that. Please open that page. So if you open that page book, 23.2, so under point A, I am going to read out what it is. The final deflection due to all loads, including the effects of temperature, creep and shrinkage, and of course measured from the as cast level of the supports of floors, because we have to measure with some reference, they are giving the reference, roofs and all other horizontal members should not normally exceed span divided by 250. This is the span divided by 250. In case of cantilever, we are not going to call this as span, instead we are going to call this as length. Okay. So what is delta permissible? So delta permissible is 3.5 meter into 1000 divided by 250. Okay. So that is equal to 14 millimeter. So actual deflection AT is less than delta permissible. Therefore, the deflection condition is satisfied. So the deflection condition is satisfied. What it means is, so we can allow up to a maximum deflection of 14 millimeter. But what is the actual deflection happening? It is only 10.15 millimeter, which is less than 14 millimeter. That is okay. So the deflection condition is satisfied. This completes this problem. So you will have to be careful, because when you are finding out the modular ratio, what kind of this Young's modulus of concrete you need to make use of. If it is immediate, you can make use of EC value directly. If you are going for long term, instead of using EC, instead you should use ECE, that is the effective Young's modulus. So then accordingly, and also once that is done, m value changes, that is the modular ratio m value changes. Once the m value changes, and then in both the cases depth of neutral axis changes. So as a result, moment of inertia changes. That is, as a result, the effective moment of inertia changes. So you should be knowing what effective moment of inertia and what values you should substitute at what time.